write in a workbook.
And to be clear, we don't expect you to implement float yourself, but the fact that you can is actually important to for data scientists. And so let me explain. When I was starting out, and I did a lot of stuff with Delphi, I guess 20-something years ago, which is like a very fast Pascal system, and I was writing a lot of numeric code, and I very often hit this floor where things weren't working the way I wanted them to, so I had to use assembler, which nobody should ever have to do, but that was the floor I hit. Like I had work that needed to be done, and I couldn't do it in Delphi, so I had to use assembler, but at least I could, you know. Yep. And over the last 25 years, we've gradually kind of filled in more and more of the things that numeric programmers use. But what I'm kind of finding is happening now is as numeric programming is becoming differentiable programming, I'm hitting the bottom of the stack again, and there aren't things that I want to do. Or there are things I want to do a little bit differently. So I feel like we're at this point in history, you know, and we might be for the next 5 or 10 years or more, where data scientists don't need to know how to write assembler, but they do need a system where they can go under the surface and actually change things that people don't normally change.
Yeah, well, and again, to me, I think the goal here is an infinitely hackable platform. So like, in the box are all the nice things you'd expect. You don't have to write map models, you don't have to write floats. But if you want to go change it and do your own, you can. Or if you want to take somebody else's, you can drop it in your workbook. You don't have to recompile the whole stack. Now, we talked about structs are a little bit like classes in Python. The major difference is that these are actually fast. So here's our square add that multiplies two things together and adds it. If this was Python, these would be allocating objects. This would be doing lots of crazy stuff. This thing I'm showing you now is called the Compiler Explorer. And you thought you came to learn machine learning. Here's some assembly language, which we're going to get away from as soon as possible. But the point is, like, you're writing reasonable Swift code, and you're getting literally the same code you would get from Clang if you wrote C++. Like, even though float is implemented in the standard library, there's no tricks here. You're getting the lowest level optimized fast code that's turning to multiply instruction and add instruction on Intel. And I'll go away from this very quickly, because we're not here to learn about Intel assembly. So now the thing about float, again, is not really about something you should want to do, but you can poke at it if you want. You can see what's inside of it. One of the things we've, at least so far, chosen not to do is we don't export the built-into workbooks, and so you have to write a standalone file to use it. We could change that if we wanted to. But one of the really powerful things about this is because these types are defined in the library, they're not magic. Well, now all the other things we talked about before work with these. And so we can add a method to int or to bool. So here, you know, we add a little isOdd method that's just saying, is the low bit set or clear? That's cool, that's fine. Like, this is not monkey patching, this is just super low level. Int is a struct, sure, you can add a method to it, no problem. We can add a symbol that turns a Boolean into an emoji, because emojis are cool. And so now you can just use these things, and we can say, hey, 4, are you odd? A4, are you odd? Turn yourself into a symbol, and we get true, false. We get thumbs up, thumbs down, and it all just kind of works.
Yeah, I mean, this is particularly important for all of us at this stage, because as we discussed, you know, Swift hasn't been widely used for numeric programming, so a lot of stuff doesn't exist. And so when I started playing with it in December, and I realized, like, oh, I'm missing stuff. So yeah, so I created this library called BaseMath where I literally was defining things on float that I needed to exist, and not only did they then exist, but they ran at C speed. And then from then on, I had all the stuff math stuff that I wanted in the language. And so if you're hacking around over the coming months and you find things not quite the way you want, you can and should change it, right? And it's really, really, really common in Swift code to add extensions to basic types. It's not at all unusual or weird. Yep. It's just part of how you write Swift code. And
you can make it feel the way you want. So we're not going to dive in too deep, but there's lots of interesting things in the system. So if you say, well, how does and work? And only evaluates one side of itself if the other side is true. Well, that's implemented in the standard library. It's 3 lines of code. You can go dive in. There's a couple of links. Let's talk about array, because we need arrays to implement matmul. Before we talk about how array works, let's look at how you use it as a Swift programmer. Arrays in Swift are super simple. You just define them with square brackets like you'd expect. Swift is type inferred, and so what you'll end up seeing is there's two different syntaxes for the types. There's int in square brackets, which is the way you'd normally write it if it's not inferred. But that is actually just sugar for this array. Okay? And if you print out the types of these things, you'll see that they're all just array event, array event, array event. Well, arrays can be iterated over, so you can have a for loop that just goes over all the elements of the array. Pretty simple. You can slice them. Swift has two ways to slice based on whether you want the endpoint or not. And if you want an inclusive range, which includes that endpoint, you use dot, dot, dot. In an exclusive range, you use dot, dot, less than, and the less than says, but not the last one. Swift supports functional programming things. And so here what we do is we use this functional map algorithm. And it's using a closure. Closures are the same thing as lambdas in Python with slightly nicer syntax. And so here what we're doing is we're saying, give me an array, but run a function that takes all the elements and adds 10 to them. And it's very simple. You can just do this right in line, and it's nice and fast. And so here we get our array where everything has 10 added to it. It has filter and reduce as well. So filter, it just takes a predicate where you say, filter and only include the things that are odd. Okay, and we just added is odd, and now we get an array that just has odd things in it. It's super easy, and one of the other things you'll notice is that Swift has lots of nice syntactic shortcuts, and so instead of naming our argument like we did in map, we just use the default name, which is $0.
So the top one is equivalent to lambda arg colon arg plus 10, right? And so then we can get rid of both the lambda and the arg colon by sticking it in curly brackets and just using $0 to refer to the first argument.
Yep. Another super common thing is that often these closures end up being the last argument to a function. If they're the last argument of a function, you can just put them outside the parentheses, and if that's the only thing in the parentheses, you can just get rid of the parentheses as well. And so you get these really nice things that are kind of like list comprehensions, where you can say map and multiply all the elements by 3, and then filter them and only keep the odd ones, and you get very nice fluent things. Or here's a map where I'm saying, you know, get the odd, decide whether it's odd and then turn it into a symbol, and I get very nice, simple.
Yeah, so just come back and have a look at this map filter again at the end of the lesson, because this is how you do list comprehensions in Swift. You don't need special syntax for it, because the stuff that's already built in very elegantly gives us list comprehensions for free.
Yep, and all these things are just library features. Reduce it's a reduction, so you give it the first element, and then in this case we're just adding all the elements of the array to 0, and plus is a function. We saw it already, and so this just uses the plus function to do a reduction. It's super simple. Now, we were talking about array. Array is a type, and that means you can do an extension on a type. So you can add methods to arrays. That's super easy. So here we defined a double elements method that returns a new array, and we just map. And so double elements just multiplies all the elements by 2. And like the self thing we don't actually need.
Oh, thank you.
Right, Jeremy?
Too much self in Python.
Yeah.
Yeah.
And now one of the other things you may wonder about is like, why do we need this where element is numeric? And what this is talking about is it's saying, well, we're taking all the elements out of this thing and multiplying it by 2. This is helping us catch errors. So if I have an array of Booleans, I get an error message that says, hey, I can't double all the elements of a Boolean array because bool is not a number. And so in Python, what would end up happening is if you accidentally pass the wrong thing in, you would pass in your bools, and then they'd get multiplied by 2, and then sometime in a far distant API call somewhere later, you find out you have 2s in your Booleans. Like, what just happened? And so Swift helps catch these errors early.
And talking of what just happened, this is the point where if you've used a few languages before, you're thinking, oh, Swift is actually pretty different in a pretty interesting way. Because look what we've just done. We've just said, here is some functionality which applies to some type which has some particular properties to it, right? So we've like defined functionality in a way that's going to be looked up in this really nuanced and interesting way. And so we're not going to go into the details now, but just like take a look at this after the lesson and think like, wow, what's going on here? Because this is something really interesting.
And again, one of the cool things about this is because it's all built in the library, it's all open to you, and you can do cool things like add methods or do other things. So I'm not going to go into the full details of array. Array is implemented right here in array.swift. This is the standard library. Array is a struct. It has a buffer inside of it, the elements. You can go through and you can see all the different gory details of things that go into array. And instead of coding this in a workbook, I think that we will just consider it that we implemented this. Is that okay with you, Jeremy?
Absolutely.
Okay,
yes.
so now we can use arrays. Okay, so let's move on to MatMul.
Okay, so what I'm going to suggest is might be a good time to take a break. So let's take a 6-minute break, and we'll see you back here at 6:47. Now that we've invented Swift and float and array, we will actually implement matrix multiplication. So we'll see you back here at 7:47. Okay, any questions before we keep going, Rachel?
Yes, we have 2 questions.
Okay.
The first is that in keyword is very unintuitive for arg and arg plus 10.
Enclosures, yeah.
Oh, can we point at that? So,
Sure.
yeah, the in keyword.
Yeah. Up here, in. Yep.
So that's the question, it's like, why is it so weird?
Why is arg in arg plus 10?
Yeah, so we carefully considered the name of this keyword, and we didn't have anything better to use, so we got stuck with this.
In Python, I guess that would be a colon.
Yeah, so there's no good answer. Nobody knows what it means. There's historical reasons, but they're not good reasons. So we just do it, and it's...
So the answer is because Chris says so.
Yeah.
Thanks for your honesty.
Like, why do we use colon? Well, because that's what Python says.
And the second question, can Swift LLVM implement instructions to execute on the GPU? Would this be a good idea?
Yeah, this is a really exciting direction. This is one of the things we're investing a lot in TensorFlow and the infrastructure pieces, and we'll be talking about that a little bit next time.
Yeah, but I mean, the short answer is that LLVM has a number of backends.
Yes.
And one of the backends it has is a PTX backend, which is the lower level NVIDIA kind of instruction set.
Yep.
And so like right now, you can compile stuff with LLVM and have it run as CUDA kernels.
Yep.
So the answer is yes, absolutely.
Yeah, and in fact, like every pixel on the iPhone goes through LLVM, not through Swift in a workbook,
That's not bad.
yeah, so LLVM is used for lots of cool stuff, and using it for more cool stuff is fun. So let's now that we have our bedrock of floats and arrays, let's build something a little bit higher level. Let's talk about matrix multiplication. So here what we're gonna do is we're actually gonna load up a few tensors, and here we're playing by the same rules that we played with in Python, where we could use the random number generation and things like this, but we're not gonna use the matrix multiplication operator quite yet. So so there's lots of ways, there we go. There's lots of ways to create tensors in Swift for TensorFlow. It has this tensor type. This little float thing, we want to go away eventually, we hope. But right now you say tensor of float to say that I want a tensor of floats. You use a shape, you can get zeros, ones, you can repeat a thing, you can get random. There's lots of different things you can play with. I highly recommend you type tab in Jupyter, and it will tell you all the things that you can do with completion. So let's build a matrix multiply. So here what we're doing is we're doing something kind of similar to what Jeremy did in the Python version of this, but here we're starting a little bit lower level. We only have one-dimensional arrays. That's how the Swift array works. And so what we need to do is we need to pass in 2 arrays of floats, and then we're doing a 2-dimensional matrix multiplication, so we need to know the number of rows and number of columns for A and B.
So that's a definition of a tuple parameter, Chris?
Yep. That's
so there are
exactly
2 ints.
Yep, so ADIMS is 2 ints and BDIMS is 2 ints. And so what we do is we create an array full of zeros, and then we write the same 3 loops you saw before. And because we have a one-dimensional array, we have to do manual arithmetic to get into it. Now, one of the things that you'll see is like if you actually try this out and you run this, oh, I didn't actually run the cell. This is why you say don't do things, and I don't listen, and then I make a fool out of myself. Okay, so then you run this, you get the tensors here. We're just using the MNIST data set because it's fun to use. Now we can run this and we can time it. And one of the major differences you'll see is we just wrote 3 loops and it takes 0.132 milliseconds. The Python version of this took 835 milliseconds.
Let's just have a look. So Chris, I just wanted to compare. So I mean, the first thing I wanted to compare is to look at the code. So that's the Swift code. And in Python, here's the Python code. So it's basically exactly the same code, except as you say,
here you have 2D arrays.
2D arrays.
Which we'll get to.
And so, yeah, we kind of found with the Python version, it took about a second to do a 5 by 784 matrix multiply with a 784 by 10. So we kind of did the math and said, like, we can't use this because it's just not fast enough. But something very different is going on here, because this is about 9,000 times faster.
Yeah. So this is not super fast, but this is pretty reasonable, and this is what you get from roughly C, right? And that's because, again, we talked about it's primitives that are principled, that are fast, and when you build things out of principled fast primitives, you get new things that are principled and fast.
Okay, so like, this is no big deal for you, but for a Python programmer, this is a whole mind shift change, because at this point, the fact that you can write this and have it run this fast means like I can now write anything I can think of doing with numbers in the most obvious way possible and have it work pretty damn well. So this is kind of like a superpower that Python programmers don't have.
Well, and if you think about it, so one way to think about Swift for TensorFlow is we're trying to subtract C and C++ out of the picture, right? Because if you think about working with Python, a lot of it ends up being, if you care about performance, working around the GIL. And how do you do that? You go into do C stuff, or working around writing, oh, I need a new kind of data structure. What do? I write a bunch of stuff in C because writing in Python wouldn't be fast enough. And that's problematic for lots of reasons, one of which is it's just really hard to do things in workbooks. But here, we're implementing basic stuff in workbooks, and it goes fast.
Yeah, and I can ship something that's like a compiled program that I just ship it. I don't have to figure out how to put the C library over here and compile it and put it together with this header.
So Jeremy, what is this built-in called time? Is that built in the language?
No. Well, so Chris,
can you show me what that is?
Absolutely. So we're not using %time because %time is a magic, and under your new rules, we shouldn't be allowed to use things that are magic. We should write them ourselves. So time is written ourselves, and it's actually written in this notebook called 00. So yeah, so when we started out with a blank slate, and so we had to start out with things like, how do I time a cell, right? So the answer is, this is the nice thing about working with Swift, is we can build everything from scratch, right? So here's the timing section, right? And the details don't matter, but basically you can see we can grab some stuff from the Swift standard library, for example, a function that tells the time, and we can run some function and see how long it takes. And the nice thing is that we can end up with some very neat syntax, right? Because the thing that we pass in, the function we pass in, is a closure, right? And this is how you say pass in some closure that takes no arguments and returns nothing at all. And so, for example, we can give it a default value, which means if we want to time something and just run it once, we can just do that, right? So we can create syntax, we can create APIs that are really nice and elegant and simple to use. And so this version of time actually is both time it and time together, right? So if you give it repeating, it'll do that, right? And actually, this 00 notebook is worth flicking through because it's the only notebook where there's no tensors in it, there's no TensorFlow in it, there's no tf.data in it. So if you just want to see like just Swift, right? This is a good way to learn just Swift. So for example, you can see how we built this thing where you can go ls.shell. So we've actually added something to string that will run a task, right? And you can kind of see how to write these things in just nice, neat, little, concise packages. And now we can export this, and now anytime you want to run a process through the shell, you can just go blah.shell. You can see how to download a file. And one of the nice things here is that you'll see that download a file, we've actually using this path library that looks almost identical to pathlib. And that's because there's a wonderful programmer, wonderful person called Max Howell. This is Max's username on GitHub. And I mentioned he's actually an open source programmer who entirely relies on sponsorship for his work. So if you like Max's work, which I certainly do, you should go to his Patreon and give him a few dollars. So thanks to Max, we have something that's really just like pathlib, but actually even almost a bit better. There's something that's almost exactly like requests. It's called just, right? So in the Swift ecosystem, thanks to the fact that you've got all these millions of iOS programmers who have been using this language for 5 years to build cool stuff, there's actually a nice non-data science ecosystem.
And while we're talking about non-data science, Python, similar packages, is there any web frameworks similar to Flask or Django for Swift
Yeah,
yet?
absolutely.
Yeah.
So,
Yeah, actually, the Swift on server community is a really vibrant community, and there's the equivalent of Ruby on Rails, and a bunch of these different frameworks have Swift versions, and that's actually one of the biggest non-iOS communities that exist.
the one I've seen a lot of love for is Vapor, I
Yeah,
think.
Vapor, IBM is investing. They have a framework called Couture, and they're putting a lot of time and thought into that. Apple has a low-level thing that's like Netty, the Netty library on Java, and there's a Swift version of that called Swift Neo. So there's a bunch of these fairly infrastructural things that exist that are part of the Swift ecosystem, and Swift is really great on servers too.
Great. So here you can see how we can download a file. It's all pretty straightforward. You've got try-catch blocks, a lot like we're used to, but they kind of do try-catch. The details are a bit different. So in this case, we want to download mlist and load it up. One thing to be aware of is that things, and we'll talk a lot more about this next week, but things can get a little bit complicated when, like for example, for mnist, we've got a file containing labels, and we've got a file containing images. They're different types. The labels are ints, the images are floats. So we kind of want two functions, one that returns a tensor of floats, one that returns a tensor of images. That's duplicate code. I hate duplicate code, right? So here's a version where we actually tell it, oh, you could load up different types of mnist data, and it's going to return a tensor of that type. Okay, and unfortunately, if I try to use this, I get an error, right? And I really wanted to show you this error because for the first week as a Swift programmer, I've never felt so stupid. Like, I felt like everything I wanted to do, Swift hated me, and it told me these things like, cannot invoke map with a what the hell is all this? And I'm just going to say that's totally fine, right? Because the Swift type system is very new to somebody like me and probably most of the people watching this. The messages are helpful for people who understand it pretty well. And it's totally normal to think, for a week or two, Swift hates me.
To be stubbing your toe on every new thing and feeling like you'll never...
And particularly this generic stuff, you know. And I would say, look, a couple of suggestions. The first is just write the two separate versions so that you don't get frustrated, and then come back and try again a few times yourself. Ask on the forum.
Stack Overflow's great.
Yeah. But quite often the kinds of errors you get from the type system are, sometimes they're even like a long way away from really where the problem was. It can be quite difficult because it's a powerful type system for it to really know where the problem is. Now, in this case, the issue basically is that we are trying to call, we're trying to initialize either floats or bytes. And so it basically needs to know that the type we're creating can initialize either floats or bytes. So as you'll learn next week, you could do that by creating something called a protocol. You do it by saying that these things conform to that protocol. You then use that protocol. And so now this version of load mnist works totally fine, right? So this is a nice little package that you can look through. The last piece that we had to build in 0.0 was the thing that makes / export works. So it's kind of delightful writing the thing that makes / export work by typing / export. One of the things that I needed to do here was to check whether something matches a regular expression or not. I found it extremely weird that the way to do that in Swift is called range of options regular expression. So I created something called find in string. So now I never have to worry about the weird and clunky Swift syntax. Most of the time I'm just looking to see whether something does exist or not. So I just created something called hasMatch that checks whether something exists or not. So I make Swift work the way I want it to.
Yep.
And to give you a sense of like when I say clunky APIs, in particular, you'll see here we're using Max's beautiful path library. Before we realized that the path library does everything we wanted, we use the thing that Apple provides, which is called the foundation library, and that comes with Swift. These two lines...
It also works great on Linux. It's a standard thing that's available.
Yeah, so those two lines of code in Apple's foundation library looks like, oh my God, it looks like this. Okay, so to me, a lot of Swift APIs look like deleting path component, appending path component, appending path extension, right? I don't know why, but a lot of Swift programmers seem to like writing this kind of code. I like writing this kind of code, but I think Foundation is not necessarily your favorite API design, Chris. Would that be fair to say?
I think it's fair to say that the thing that's great about Foundation is it has a lot of interesting and useful stuff, like URLs and other stuff like that, but its design is not all great.
It's great that it's there. And it's amazing that it's all been ported to Linux, right? So quite often you'll find...
It's got a tremendous amount of function.
I need something like, you know, the ability to tell the time. It's in dispatch. Or the ability to work with URLs. And so know that Foundation is there. And generally speaking, I always just import it first thing, right? Because there's a lot of stuff you want will live there. And if you forget to import it, it won't appear in your tab completion and you'll get errors. But also, when you find clunky Foundation APIs, which is most of them.
There's usually a better one out there.
Or write your own little wrapper on top. Anyway, so once you've done that, now we've got our own, you know, JSON serialization thing. We can grab our Jupyter notebook, we can find our cells, we can export them, and now we can just do the same thing that we do in Python. And we now have a nice little module exporter that we can use.
It's cool.
We have a question on the time function. How do we know that calling f parentheses is not optimized away in this case because of a lack of side effects detected by the compiler?
Generally, so that's actually a great question. In the case of the workbook, I don't think there's no cross-workbook optimization going on, so that's one thing. I don't know if there's a really good... Wait, that's a good question. What I recommend doing is put something that's not trivial inside the thing you're timing. And so if you're doing, you know, we'll show you later, launching a CUDA kernel to do a matrix multiplication, for example, and that's not something that gets optimized away. You can also like get the value into the closure and then take the value back out. So there's different things that you can do like that.
Yeah, sometimes when I was doing this stuff for base math, I would just add a print inside the thing that I was timing to force it to be calculated.
And one of the other things that will happen with GPUs is GPUs run asynchronously, and so you need to force a GPU sync. And we'll show you how to do that in a minute. So anyway, so coming back to this, so we showed you how to build matmul, we showed you how to build time. So this matmul is working on arrays, and this is pretty fast. We talked about it's 0.13 seconds, but array in Swift is safe. And so what's happening is that every time you like index into an array, it does a check to make sure that the index that you're computing is in bounds. And so this is actually doing a lot of work that you would not need to do if you're in C. And so one of the other really cool things about Swift is that you can actually go all the way down to the bare metal and do things the unsafe, nasty, awesome C way if you want to get even a little bit more performance. And so here, sorry, I forgot to change this back, but we have a couple of arrays, and so we have the exact same signature that we did before, where we take in two arrays and we have our dimensions. And so what we're going to do is to optimize storing into that result array, we're going to say, give me an unsafe mutable buffer pointer into that array. And it's unsafe, it's verbose, it has red warning signs all over because it's unsafe. But with almost no code change, now we're able to get something that runs twice as fast. And so here's matmul, and now it runs at 0.07 milliseconds, which is even faster, which really is the performance of C. And this is pretty cool.
And something I found with base math is like sometimes these differences are 4 or 5 times faster because making something a pointer allows it to use SIMD vectorization. Yep. So it's like it's not a minor tweak. You can get super fast performance.
But the thing I want to emphasize at this point is that this is like a super low-level geeky thing that not everybody should do. Right? This is something that it exists because at certain points in your career or your journey, you may find that it's useful, or you may find something that somebody else wrote and it going twice as fast as it otherwise would is a pretty big deal because it makes you twice as productive. But usually you're not working at this level. Like layers are a good thing. If you want to go like super deep down the rabbit hole, unsafe pointer and unsafe mutable buffer pointer and all these things are also Swift libraries, and you can go see their implementations too. And those are implemented in terms of the Llvm magic, just like Float is. So at this point, let's skip over more C stuff and jump down to working with Tensor. So we've got a matrix multiplication working on arrays and floats, But we also have tensors. And so when we talked about tensor and matmul in the PyTorch context, you started out by using the tensor abstraction as the thing that was the container for the matmul. So let's talk a little bit about how tensor works, because this is the first really Swift for TensorFlow piece of this. Tensor is a type, and tensor can have multiple different elements in it. Like we talked about before, you can create one with zeros or with random numbers. And the nice thing about tensors is that they carry a shape, just like you'd expect. And so you can get it with dot shape. So here you can see we have a 5 by 784, just like you might expect. And here we have a two-dimensional tensor, and you can print it out, and it's a two-dimensional tensor, just like you would kind of expect. Python has the @ operator to do matmuls of two tensors. Swift has the same thing, but it uses the nice Unicode thing. There's an easy way to type this if you're on a Mac, or if you're using the compose key on Windows. Or if you don't like Unicode, that's also totally cool. You can just use the matmul function and just spell it out. And so, this is an example of Swift just wanting to work the way you want to work. And if you like math, then you can have math. If you want to type things out, you can do that too. And they're both great. Tensors do all the basic stuff you'd expect. You can reshape them with the reshape function. They support square root and all the other math stuff. It all works the way you'd expect. It has element-wise operations like add and multiply and square root and pow.
No, we have a question from earlier.
Yeah.
Why was it unsafe, what you did?
So what we did was we turned off bounds checking. And so if I write code that, if I have an array of 10 numbers, and in Swift, if I access out the 11th element, it will explode and tell me that that's invalid. If you use unsafe, then it will let you do that. And so whatever happens to be in memory beyond the end of your array, you're now poking at, and you should not do that, but you're taking the guardrails off. And so this is, Swift is trying to be by default safe, and it's trying to help you. It's trying to check things for you, but if you want to, you can just rip off all the guardrails, and just like we showed you with Python, like you can literally do things as dynamic as Python if that's what you'd like, but the defaults are there to help you out.
Yeah, so Python programmers, a lot of them won't be familiar with this idea, but in things like C, unsafe code is code where you're working with memory that hasn't been initialized or it's been freed, and it's a really big problem if you're using it like in production or something, because that kind of thing is how people can like inject shellcode into your server and
security
take over and steal your users and whatever. So, you should, I think it's fine in our Jupyter Notebook though.
Yeah. So, so coming back to tensor, you can add them, you can multiply them, you can square root power, like all the normal stuff you'd expect is on tensor. Tensor also, if I run the right cell, tensors also have a bunch of methods that do cool things like convolutions and other stuff like that we'll talk about later. One of the interesting things about Swift is that it likes comparisons to return Booleans. And so you'll see that if you compare two tensors, it will see if it will give you an ordering of the two tensors. But sometimes you want to get a tensor of Booleans back. And so Swift calls these the point-wise operators. And so if you put a dot before the less than or the greater than or the equals or whatever, it will do a tensor comparison.
Yeah, and I get burnt by this all the time in NumPy and PyTorch that doesn't have this level of consistency. So I think this design call is awesome, this idea that Boolean operations always return Booleans and point-wise operations return point-wise Booleans.
Yep.
It's a good idea.
And then you have reductions like any and all that say, hey, if I have a tensor of Booleans, I can check to see if they're all set or if any of them are set.
So basically then, I mean, the next part of the notebook is just saying, hey, look, all the stuff that you've seen before looks exactly the same as what you've seen before. Sometimes the words change, like unsqueeze is called expanding shape at, which is a rather Swifty way of saying things. But there's, in a lot of these notebooks, you'll find that there's like lots of details where we've just basically copied the Python code, and we're not going to show you all those details because they're the same.
Yep. Now let's talk about matmul on tensor. So what we've done here is we've defined the same matmul that we had before, and before we took two arrays and we took two dimensions. But tensor carries a shape, and so here we implemented matmul on tensor. We start by creating a zero tensor, we loop over it all. Now we have our two-dimensional indexing, just like you saw before with NumPy. When you run this, what you'll see is this is a lot slower. This takes 7 seconds to do one matmul, where before it was taking 0.07 milliseconds. So Why?
So it's about, so what is this? So this is about
It's thousands of
10,000 times fast,
Yeah.
slower. Yeah.
So why is that, Jeremy?
Why is that? Well, the first thing I want to say is that hopefully at this point you're thinking this is a problem, because it's kind of like the exact opposite of everything that Chris has been telling us and I've been telling you about why this is good. Like, what's the point of something that's infinitely hackable if there's this TensorFlow layer we can't go beneath, and that it's so slow that we can't really actually write things that run, 7 seconds through a small matrix multiplication? Extraordinary. So we would not be running this course if this is where we were heading.